back in your head. What's the vertex of y equals x squared?
The origin.
And if I add a number, what's the vertex of y equals x squared plus 4?
Either 0, 4, or 4, 0.
Which one?
1 of them.
0, 4, because there's no number in brackets. Okay, no number in brackets, so we just take the number at the back. What's the vertex of x squared minus 2?
0 minus 2.
What's the pattern? What's happening there?
It's moving a little bit.
More specific, which coordinate is moving? It's the y coordinate. And is y the vertical axis or the horizontal axis? It's the vertical. So in general, if I just call this number q, what's q? Just any kind of number. It's just a variable. This we call a vertical translation. We didn't use those words last year, but that's what was happening as we were pushing this parabola up or down. And so I'm going to put the arrows for the visual people. This can be up or down, not left or right. Well, what happened when I added or subtracted that number in brackets? So what's the vertex of x minus 5 in brackets squared?
5, 0.
Why not negative 5?
Because the formula. Because no.
Yeah, it's that opposite thing we talked about last year about how if it's minus, it's actually to the right, and if it's positive, it's actually to the left. Same deal here. So what do you think x plus 7 squared is going to have for a vertex?
Negative 7. 0.
So if I just call this letter p, again, p is just a variable, just meaning any kind of letter. This is called a horizontal translation. Can you turn your sound off? Again, we didn't use those words, but that's all we were doing. And this is your right or left movements. These transformations are called translations. And they can be applied to any kind of function, not just quadratics. We're going to do so many fun functions today. Translation, and then I put a little arrow to the left and arrow to the right.
Why didn't they teach us a simple 12-letter word in grade 11?
I know, because we didn't want to scare you. Listen, there was so much in grade 11.
It's 12 letters.
That's scary to a lot of people. Like to a mathematician, that's the multiplication of 12 variables. Think about that.
Luckily for them, it's English, not math variables.
Ah, but is math a language? That's an interesting debate. Is math a universal language? Another interesting debate. How do you know the difference between a vertical and a horizontal translation? I'm going to repeat this 5 bajillion times between now and the end of this unit. Vertical translations are outside of brackets. And again, they're your up and down movements. Horizontal translations are inside brackets.
And they're the opposite of what the equation says they are.
Correct.
You should probably write that down as well.
It's going to come a little bit later. Here's the different kinds of questions you're going to see in the homework. The first thing we're going to do is just describe the transformations. So we're not going to actually graph them, we're just going to talk about them. The second thing is we're going to write an equation after it undergoes some kind of transformations. And then we'll get into sketching the graphs.
Will we get into any poorly written questions where we can get full marks for saying that we know nothing?
No. Although I did notice I started today with, tell me everything you know about parabolas, and nobody said nothing. Shame on you. Shame on you. -1 off your next test. Here's a cubic function. This is probably your first time seeing a cubic. How did I know it was cubic? Just by looking at it.
The little fruit
The little 3. So just like you know a boy when you see a boy, and you know a girl when you see a girl. Sometimes we're not sure, but let's say in general we know. You know a parabola because it has an x squared. You now know a cubic because it has an x cubed in it. What's this?
That's root.
Yes, and what kind of function do we call this? It was the last unit in grade 11.
Radical?
A radical function. So you know a radical because it has a root sign. If you forgot that word, jot it down. It's called a radical function. All I've done in this example is put in some translations exactly like we did with parabolas. I've just put a cubed and I've put a radical.
And the f of x is just another way of saying y.
High five. So describe the transformations. I'm going to start with the -2. The first thing you do to describe is tell me whether it's horizontal or vertical. Then you tell me what kind of transformation it is. Then you describe how it changes the graph. If it is inside brackets, it's a horizontal. It's an adding or subtracting, which means it's a translation. And this would move the graph 2 units to the left. There is describing the transformation with using absolutely no words. So describing math doesn't mean you're writing down a whole paragraph telling me, no, it's just a code. It's an HT, which stands for horizontal translation, 2 units to the left. Why is it to the left? Because it's a +2, and positive go to the left, negatives go to the right. Now I'm going to describe the -5. Again, you tell me the direction, its name, and how it moves. It's outside brackets, so it is vertical. It's an addition or subtraction, which makes it translations. And this one is going to go 5 units down. That is describing the transformations. That's it.
And I'm guessing we'll learn what it is if it's multiplication.
Yes, and you actually already know with parabolas. Same thing, even though it's a radical function, I'm going to grab the 3 first. Is it inside brackets or outside brackets? That means it's horizontal. Is it an addition, subtraction, or a multiplication, division? It's an addition, so that makes it a translation. And it moves 3 units to the right. So just grabbing my red pen, just making a note off the side with horizontal translations. Positive numbers go to the left. Negative numbers go to the right. I just realized my little arrow could mean a direction. I just meant positive goes to. I probably shouldn't have used an arrow. So it's a little bit counterintuitive because your brain sees a plus and it seems like that should be on the right because those are the plus numbers. It's kind of backwards with a horizontal translation.
Yes, so there's a right arrow right next to it.
Yeah, I probably shouldn't have used arrows.
Right.
Right.
Left.
Right. Let's do this -5. Is it inside brackets or outside brackets? That means it's vertical. It's a subtraction, so it's a translation. And it is 5 units down. Do you understand how to describe a translation?
Yes.
Okay, so you tell me the direction, its name, which is translation, and what it does to the graph. The graph of y equal to x cubed is translated 3 units up and 2 units to the left. Write the equation after these transformations. What it wants you to do is write me something like this. Something like 1a, except we're going to change the numbers, and we got to figure out where does the 3 go, where does the 2 go. So I'm going to start with the general, I still have my red pen, don't want it, the general form, which is y equals. I'm going to open some brackets and put an x and put my cubed. The question is asking is what's the number that's going to go in the brackets and what's the number that's going to go outside the brackets. That's what it's really asking you to tell me is where are these numbers going to go. If it's 3 up, what direction is up? It's vertical. So does that number go inside brackets or outside brackets? Outside, if it's going up, is it a +3 or a -3? If it's going to the left, is that horizontal or vertical? Horizontal, is that inside brackets or outside brackets? Inside brackets, if it's to the left, the value is +2. That's what the question is asking. Write the equation after transformations. It's x + 2 cubed + 3. How are we doing so far? Okay, now we're going to do the actual graphing questions. Sketch the following graph. State the domain and range. Andrew, I'm putting you on domain and range duty because I always forget. So you may not let me go on to the next question unless we have done domain and range. Got it?
Got it.
Method off to the side for the method wordy people. Step 1, sketch the base graph. I'll tell you what that means in a second. Step 2, describe the transformations. Good luck, guys. That's why we practiced in step 1 describing them, because we need to describe them in order to graph them. Draw the transformations. That's not nice. Notes. We've talked the last few units when I write note and I get excited and I highlight it and it's in red and I underline it. What does that mean? Like it's probably really important stuff. Your last drawing. Must, and then I get excited and I underline that because must means must, not an option. Not if you feel like it. Be in red pen.
Why red? Why not blue?
Because I say so is really the answer. It's my rule, and the reason is when we get further on in this unit, sometimes we're going to have, for example, 5 or 6 quadratics on one set of axes. And if you've made a mistake, I have no idea which is your last graph. I cannot find it. If the last one is red, it sticks out, and I can work backwards to try to find your mistake. If nothing is in red, I can't find anything, you get 0. If something is in red, the last graph, and I can work backwards and find your mistake, maybe you'll only lose a half mark. Red means red to me because I'm visual, so I need it to stand out. It doesn't mean orange, it doesn't mean pink, it doesn't mean crayon, it doesn't mean black with a note saying this should be red, because I've seen everything. Red means red. It's because I'm visual and I need it for your graph to stand out.
What if you're marking someone else's provincial exam from another school and their teacher didn't?
I ask not to get the transformation questions because they give me headaches. Because I'm so, like you're going to see, we're going to have so many graphs, if there is a mistake, it's impossible to find. It's impossible. I'll show you in a second. Bear with me. Step number 1 is what's called the base graph. That's like y equals to x squared. There's no other numbers, there's no vertex, there's nothing going on. Y equal to x cubed is a base graph. So what you want to do is take away the numbers and tell me what is left in this graph. So if I take away the numbers, I'm still going to have a y, I'm still going to have an equal sign, I'm still going to have these funny vertical lines which are called absolute value, and I'm still going to have an x. That's called the base graph, is take away all those transformations, what would you have started with? Now, if you don't remember what absolute value looks like, we're going to start with the table of values, but you really should memorize this after you've done a couple. So if you're ever stuck on the exam, always go back to table of values. It'll help you get the base graph. I'm just going to pick some random values of x. We typically pick -2, -1, 0, 1, 2. We like to see the left. We like to see the right. Again, you can pick any numbers you want. It doesn't matter. Those are typical. And we sub them in and see what happens. So if I sub in -2, what's the absolute value of -2? What's the absolute value of -1? What's the absolute value of 0? What's the absolute value of 1? And what's the absolute value of 2? So let's graph it. Does anyone remember before we graph what it looks like? Kind of. It's the V, if you remember from last year. Parabola was the U, absolute value is the V, so you'll see in a second. So first point, -2, 2.
Easy way to remember that. Absolute value.
Ooh, I like that. It's got a V in it. Later on in Unit 4, there's a W. Can't talk about it now. Make sure you have arrows on the end indicating the graph goes on forever. That is the base graph of absolute value.
Is it supposed to be in red?
It's not my last graph because I haven't done the transformations yet. Good catch, though. By the way, the other graphs, I don't care what color you use. I don't care if you do them all in pencil, all in pen. If you trade up colors like I do, I don't care. I just care that the last one is red. And again, it's for your own benefit, because if you make a mistake and I can't find your graph, there's nothing I can do with that.
But if the initial one's in yellow,
I'm okay with that.
even if the yellow's too bright for you to be able to see.
I'm okay with that.
Any color but black.
Just any color but red. Red is the last one.
For example, I always use black, so if I have blue, which may be easy to get, I'll try to get a red pen, but if I have blue.
I have a bucket of red pens, like right here. Like I have markers, I have pencils, I have it all.
I was saying, because one day I'll like forget.
And that's why I have a bucket right there behind my monitor.
What about come the exam?
You will bring a red pen. If not, I will hurt you. Second step is defining the transformation. So we're going back to the question and we're saying, what is this 3? Well, you ask yourself, is it inside brackets or outside brackets? Which means it's horizontal. It's an addition, so now you know they're called translations. What does it do to the graph? It moves it 3 units to the left. I'm going to show you 2 different ways to graph the transformation, and then from there on you can pick whatever method you want. The first one I'm going to call counting method. Grab your red pen, because we only have 1 transformation, so this is going to be our last graph. And again, I know it sounds stupid now when there's only 2 graphs that one has to be in red, but when we have 4, 5, 6 on the same set of axes, you're going to be happy your last one is red. Counting method is I'm going to take those 5 points, and I'm going to just count 3 units to the left. I'm not going to move them up or down. I'm just going to move them to the left. So I'm going my point here, and I'm going 1, 2, 3, and it's ending up at -5, 2. Yeah, the flower bucket, the red flowers right here behind my monitor. Then I'm taking that second point and counting 1, 2, 3, and he ends up at,
I'm so
yeah, a little bit of red, color-coded. Come on, left brain. And I'm going to take at the origin, I'm counting 1, 2, 3, and he ends up at -3. And the fourth point, 1, 2, 3, moving him over. And the fourth point, 1, 2, 3. Grabbing my ruler, I'm going to join those new points. And here's our first transformation of an absolute value graph. You know, a few minutes ago on the floor when I was like, move yourself up, move yourself down, that's what we did with this absolute value graph, is we picked it up and we moved them over. That's what a translation is. I'll show you method 2 in a second. The last unofficial step that I didn't write here because it's for visual people, so if you're not visual, this isn't going to work for you. Visual people, what I want you to do is look away, look back, look at the red graph. Can you see that you took that blue graph and moved it over 3 units? At the end, you always want to look away and look back, because again, sometimes when you're doing 4, 5, 6 graphs, you lose track of what's going on. So always at the end, look away. Did I do a horizontal translation? Sometimes you'll look, you're like, whoa, I moved that up. But if you don't take that time to look away and look back, you'll miss it. So again, it's for visual people. If it doesn't work for you, don't worry.
Don't forget the domain and range.
I'm not done. I'm going to do second method, then I will do domain and range. The second method, if you like to work off the table of values better, then do it. This says it's a horizontal translation of 3. What that means is we are minusing 3 from every x coordinate. So what is -2 minus 3? -5. What is -3 minus 1? What is -3 and -0 or +0? And what's -3 plus 1? I can't believe you didn't pick up on that either. And -3 plus 2? And then you can just draw these new coordinates. So if you plot -5, 2, followed by -4, 1, followed by blah, 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 you'll get where the red graph is.
Does it, like, it has to be set like that? Like, okay.
That's where it is.
Okay. Will most of our graphs just be these then?
Nope. We're going to do cubics, which we'll see in a second. We're going to do absolute value. You didn't catch on, Andrew, when I said -0. You didn't even comment. Okay, domain and range. I'm going to stick on the bottom here. Remember domain and range from last year? What's the definition of domain? All the possible x values. Definition of range is all the possible y values. What's the easiest way to remember that? What comes first alphabetically, domain or range? Domain, the word domain comes first alphabetically. What comes first alphabetically, x or y? X. So domain goes with x because they're both first alphabetically. Range goes with y. Just a little way to remember. So we're looking to the left. What do we know about this arrow that's going on forever and ever and ever? negative infinity. And on the we look to the right, on the positive side, it's going all the way up to infinity. Remember last year there were two ways to state domain and range? Okay, so I'm going to give you both ways. You pick whichever way you want. We can call it negative infinity to infinity with round brackets. If you don't like that, does anyone remember the other notation? You probably wrote it 100 times. XER. The E has to be a curvy E. It's like a C with a slash. And the R has to be a double bar because these are not letters. These are characters. They're symbols. What does the E mean? Is an element of. That one little symbol means is an element of. What does the capital R with the double R mean? The real numbers. Okay, so these are characters. They're not words. So you can't make it look like a different kind of E. The range, so you're looking down first. Where does the graph stop? Well, there's no graph down here, so what is its lowest value? It's 0, and the arrow's going up means it goes on forever. So you have two choices. You can match the first notation, which would be 0 to infinity. If you like the YER better, we would write that as y is greater than or equal to -0. Shame. You can have either the first two or either the second two. You can't mix and match. You can't have a negative infinity infinity with a y greater than or equal to 0. You can't have an XER with this guy. It's like speaking two different languages. Whew, domain and range. There was a quick review of a 2-hour lesson in grade 11. Cubic. Note. Oh, you're on to me here. I know, because it's not like as important as the other, but it's still important. Y must be isolated. Y? Yes, that's right. If you don't isolate that Y, you're going to think that vertical translation is something else. So anytime you see that Y is not by himself, we want to leave him all alone. He's antisocial. He doesn't want friends. He doesn't want that one with him. How do we move the one to the other side? Subtract 1. Step 1 is drawing the base graph. Strip away all those kinds of transformations. The base graph would be Y equals. The brackets would go, the -2 would go, the -1 would go. All that would be left would be x cubed. So this is a base graph of a cubic function. Again, this is your first time seeing a cubic, so we'll start with table of values. You can always go back to table of values, but you'll see in a second, once you draw a few of these, you're going to know what it looks like. Just like a parabola, you know now what the base parabola looks like. Again, you can pick any numbers. We tend just to pick -1, -2, 0, 1, 2, because we like a little bit on the left. We like the origin. We like some on the right, but it's completely up to you. Oh, shame. Okay, I'll do it this once. That's it. I don't like it either. I don't like it. We sub in. So -2 cubed. So -2 times -2 times -2. -8. At -1 cubed, so -1 times -1 times -1. At -0 cubed would be -0 times -0 times -0. 1 cubed? 2 cubed? Okay, so excited. -2, -8, way down here. Okay, stop. What do you think it's going to look like? Don't spoil it when you already know. So the U, we got the V. Okay, okay. -1, -1. 0, 0. 1, 1. 2 way up here at 8. We call it the snake. There's your first cubic function. We call it the snake. No, because they're not lines, they're curved. I call it don't connect the dots. So you never with a ruler want to come in and connect the dots. They always have swoop to them. And we'll talk in Unit 5, why do they have swoop to them?
Don't even think about connecting.
No connecting the dots.
Do not even think about it, simple.
Yes. Don't let me get into a whole thing about lines versus curves. You're not going to like it. Step number 2. So what was after drawing the base graph? Describe the transformation. So let's go back to this question. Let's grab this minus 2. Inside brackets or outside brackets? Inside, so that means it's a horizontal translation. And it's going 2 units to the right. Why is it to the right? Because it's minus 2. And this minus 1 at the back, inside brackets or outside brackets? So that means it's a vertical translation, and it's 1 unit down. I'm going to do the horizontal translation first, and I'm going to do the vertical translation after. How do I know? Because I went from left to right. So I'm not grabbing red pen, because this is not going to be my last graph. I'm going to pick, they would pick purple, but somebody stole my purple pen. I'll pick green. Left brains understand, I'm sad my purple is gone. Oh, those are pens, not like my lovely felt pens. Like these are like felt, I love these pens. I'm going to take either every point on the graph and move it 2 to the right, or I can work off here if I want to. All I need to do is add 2 to the x if I want to do it with the table of values. So negative 2 plus 2, and negative 2 minus 1, and 0 plus 2, and 1 plus 2, and 2 plus 2. So if you like the coordinate method, you can just plot those new coordinates. If you like the counting method, join me over here. I'm going to grab every point and just count 2 units to the right. Swoopy shape. It really depends on how you learn. Visual people, they can get caught up in this when there's a lot of graphs going on. There's so much going on, sometimes your brain can't separate them. So then they might want to go to coordinate method. Sometimes non-visual people don't like this because it's visual. They like to go with the coordinate. It completely matters with your brain. And as you do examples, you'll find out which one you like better.
I like that, but I was saying like, sometimes there'll be so many that
Nope.
it'll be harder.
It will not fail you. Either one will not fail you. Now I'm going to do the vertical transformation. Again, if you want to go to the coordinates, we're now going to y and we're minusing 1. So negative 8 minus 1, negative 9, minus 1 minus 1, 0 minus 1, 1 minus 1, and 8 minus 1. Kind of silence there, 8 minus 1. So then you're graphing the green with the red. If you're a counter, come with me over here. I'm going to the green graph, so not back to the original. I'm going to the next graph, and I'm just going to move everything down 1. So the negative 8 is going to go to negative 9, down 1, down 1, down 1, down 1. I didn't move it side to side. I just dropped it by 1. Join in the snaky shape.
So which colors is it with? For the last graph that we just did, is it which colors, like the green ones?
The green with the red. So I always work the outside. Okay. So the outside of the x, the outside of the y is what you're matching up. Look away, clear your eyes, look back. Look at the base graph, look at the red. Did you move it over 2 and drop it down? Translations are the only transformation that I will let you draw 2 graphs in one. If you wanted to not do the green graph, I'm okay with that. If you just wanted to have the base graph, and then you want to do your counting in 1 step, so every point you're counting over 2, down 1, I'm okay with that. Do not do more than 1 transformation if it's not translations. When we get into what's called the stretches compression, the reflection, if you're trying to do more than 1 per step, you're going to screw it up. So translations are the only one that if you want to double up, so not have this green graph, I'm okay with that. I'm not okay with that in any other kind of transformation. And I'll show you what I mean when I get down to this one down here. Are we okay so far?
So we do the base graph, and we never really touch that again.
Correct. It's just to be able to move it. That's the only reason we have the base graph, is to be able to count and move it over. So again, if you wanted to do every point and count 1, 2, down 1, 1, 2, down 1, and not have this green, I'm okay with that. Other transformations, no, you need to do them step by step for your own good. Oh, what kind of graph is B here? Which apparently is C. Where were you, Andrew? It's a good thing we got a backup over there. Look to the left. Look to the right. Conclusion?
XER,
Or if you want the other notation, what would you write down?
some crazy infinity.
Some crazy infinity stuff. Negative infinity, infinity, round brackets. Look down. Look up. Because domain is down and up, right? It's the bottom and the top. Or you could have negative infinity to infinity. If you're like, what domain? Come and see me. I will walk you through domain slower. Show me your thumbs so far. How are we doing on translations? I'm getting it. I'm kind of getting it. I'm not getting it. Put it really high, really, like as high as you can reach.
What would the other range be?
Negative infinity to infinity. It would match the domain. It would be exactly the same. Really, Gunther, too lazy to raise your arm? Like, really? Nice.
Yeah, it's Friday afternoon work.
Let's do a radical. See if you remember from last year. First thing should jump out at you. Oh, Y is not alone. Y is not alone. Y is antisocial. He likes being alone. How do we get rid of the -2?
Plus
Base graph is take away those transformations. What's going to be left is the Y, the equal sign, the root, and the X. That's called the base graph of radical X. If you don't remember them from grade 11, we'll do a little table of values. Now we got to be a little bit smarter here in the x's we pick. I'm not going to pick -2 as my first one, because what is the square root of -2? It doesn't exist. I'm not going to use -1 because the square root of -1 doesn't exist. Can I use 0? Okay, so let's start with 0. What's the square root of 0?
But we can't use -0. The square
Can't
root-
use -0, doesn't
square root
exist.
of -0 doesn't exist.
Can I use 1? Okay, square root of 1 is? Now I could use 2, but the square root of 2 isn't a perfect square. It's hard to get without a calculator. So what would be the next best choice for my x value? 4 is a great choice because the square root of 4 is 2. Let's get one more point. What's the next best choice? Square root of 9 is 3. So I'm just going to highlight these x values just to bring attention to them later, that we chose them because they're perfect squares. Again, you can use other values, but then you got to get your calculator, you got to figure out it's just nasty. Just use your perfect squares. Anyone remember what the rational or radical graph looks like? Okay, 0, 0, 1, 1, 4, 2, 9, 3. He is half a parabola turned sideways. We call him the swoop. Mathematicians are not creative people. Not so much.
What do they call this then?
The swoop. The swoop. Sometimes a swoosh. Don't like that one so much because I think the Nike swoosh, which looks different. It's a swoop to the right.
Just go half the way.
So it's half a vertical parabola.
It is half a horizontal parabola, we call it.
Oh, okay. What's a whole horizontal parabola?
That's when you get your plus or minus square root, which we'll talk about later on in the unit. Ooh. What was step 2 after drawing the base graph? Okay, so I'm going to grab the 4. Now, you need to understand there are times, mathematicians, we are really picky people, and there are times we are really lazy people. We are lazy people with radicals because there are assumed brackets. We just tend not to write them. We assume that this means the radical of all of x plus 4. And so there are actually brackets there, and that might help you understand what's vertical versus horizontal. So just know anything under the root, there's brackets that we tend to get lazy and not write. Having said that, is that for inside brackets or outside brackets? Is it inside the square root or outside the square root? So that is a horizontal translation. 4 units to the, I heard both at the same time. Why is it to the left? Because it's positive. Do you understand what I mean by the brackets there and we're lazy? Okay, so inside brackets or inside the square root, same thing. The 2 on the outside, is it inside brackets or outside brackets? Or is it inside the square root or outside the square root? 2 units. This one I'm going to do both of those in the same graph, so then you can see if you like doing them separate like the last example or you like doing them together. It's completely up to you. I'll do the coordinates first for the coordinate people. We are minusing 4 from the x's and we are adding 2 to the y. So the first x value is going to become minus 4. The next x value would become the third x value and the last x value. And then the first y value would become followed by, followed by, followed by. Grab your red pen if you're going to use those and plot those new points. If you're a counter, come over here with me with red pen. I'm going to take those 4 points that we had. I'm going to count every single one, 4 to the left and 2 down. So I'm just doing both transformations in one step. So starting at the origin, 1, 2, 3, 4, 1, 2, up. The next point, 1, 2, 3, 4, 1, 2, up. The next point, 1, 2, 3, 4, 1, 2, up. Seriously, it's just counting like kindergarten. 1, 2, 3, 4, 1, 2, up. Oh, and I totally missed that one. Failed counting. Make sure if there's an arrow on the right of the base graph, there's an arrow on the right of the new graph. Make sure if it ends and stops and there's a stopping point, there's a stopping point on this one, so it matches up with the base graph.
And that's like when you skip
Yeah, so I skipped the green one. If you're comfortable with that, great. If you're like, I don't want to, then you could do one of these before the other. You'll see when we get into stretches and compressions, you don't want to start skipping, especially if you're left-brained. Yeah. No, this is completely up to you. Just a method. If you like counting. Who likes writing it out? Who likes coordinate method? Who likes counting method? Yeah, it's usually split. Look away. Look back. Look at the base graph. Look at your red graph. Did you pick it up and move it 4 units to the left and 2 units up? Questions so far? One more to go. Thank you. See, I always forget domain and range. That's good. Look to the left, and then you're going to the red graph, by the way. So you look to the left. What's the lowest possible x value? Where do we run out a graph? -4. Where do we run out a graph on the right? Well, the arrow means forever and ever and ever. If you like the other notation, we're going to say x is greater than or equal to -4. Now you're looking down, so you're looking on the y-axis. Where do we run out a graph? What's the lowest possible point? 2. What's the highest possible point? If you want to do the other notation, y is greater than or equal to 2. We good? The last example I put in, because there's one like this in the book and everyone freaked out last year, I called it working backwards. They're going to give you the graph already with a bunch of transformations, and they're going to ask, what was the original graph? They're going to give you a base graph. They're going to give you a graph, sorry, before or after a bunch of transformations. They want to know, what did we start with? Sometimes they're not going to use a cubic or a square root or an absolute value. They're going to give you what I call a funky graph, and that's why I didn't draw it, because I wanted you to draw it with me. So imagine this is what the book gives you, and I'm making this up out of my head, so put some points with me. -4, -4. Let's do -2, -1. -2, -1. Let's do 3, -1. And let's do 6, 3. Where did those come from? I made them up. The book would give this to you. And we're going to join it with straight lines just for Gunther, who likes his connect the dots.
Can you write those numbers down?
Was it 6 and 3 the last one?
Do you mean could I or could you if you wanted to?
Was the last one?
Does that do it for you?
Yeah.
This is what I call a funky graph because it's not one of our normal base graphs. It's just a made-up graph because they want to know is can you apply these transformations to any kind of graph. So the book would give you this, and they're telling you this is f of x minus 2 plus 3. This is a graph after some transformations. They want to know what did we start with. They want you to go backwards. They want you to move it back to where it would have been before we did all these things. Do you understand what the question is asking for? So we're going to figure out what the transformations were, and we're going to do them backwards. The -2, inside brackets or outside brackets? So that means it's a horizontal translation. It would have been 2 units to the right. The 3, inside brackets or outside brackets? Means it's a vertical translation. 3 units to the up. Hello. What? It's a good day for you.
Thumbs up on this. I'm hunting a student.
Oh, very good.
No, math.
Math. We need to go backwards because the question has told you to go back to the original. So we're not going to go 2 to the right. What are we going to do? We're going to go 2 to the left. We're not going to go 3 up. We're going to go 3 down. And we're only reversing them is because we're going back to the original. I don't care so much for this one when you're drawing the original graph because there's only one. I don't care. So if you want to work off the coordinates, you can work off the coordinates. If you want to count, you can count. Completely up to you. So now I'm going 2 to the right, 2 to the left, 1, 2, 3 down. 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 That made a really cool pattern. Again, just like before, if there's an arrow on one side or both sides, you match it. If there's not an arrow, you match it. So I put no arrow on the left, but an arrow on the right because that's what was given in the question. Question didn't say, so we're okay. We didn't do an example like this and people were freaking out when they did the homework, so I wanted you to see a working backwards one.
There's a parallelogram on there.
It is a little parallelogram. It's kind of cool. I think that's it for today.
We know nothing